Hi, everybody. As Ewan said, we are from Blizzard Entertainment, and we're going to talk to you about how we use Kafka within our data pipeline. First, we just want to do a show of hands. How many of you have played a Blizzard game? Okay. Yeah, so that's a few of you, I would say, maybe a couple. We're a small indie shop. Not a lot of people have heard of us. So I am Jeff Field, systems engineer for big data at Blizzard Entertainment.
I'm Dustin Koupal, systems engineer at Blizzard Entertainment, and we're part of a team of 25 called the Global Data Platform Team. We're responsible for all sorts of things like SDKs that our different game teams will to embed into their server code so they can send us data. We have a Crashlytics system built on top of HBase. We support near real-time analytics systems and alerting systems. But Jeff and I are part of a kind of a sub-team that we internally call ourselves the Data Gnomes. Formerly, we're known as the long-term analytics team, and we primarily focus on Kafka and HDFS. We were originally a temporary team where they kind of pulled people from a whole bunch of different departments. Jeff and I are from IT. We also have some SREs that joined us from IT, and some more traditional engineering type people came together to support the launch of Overwatch. And as everyone knows, the quickest way to permanent is temporary, so we're still a team, and we're still doing that.
So in the beginning, the data pipeline story at Blizzard started, as it did at a lot of companies, as Perl scripts running on desktops, querying databases, and then ETLing that data into a data warehouse that at that point was probably like a relatively beefy Microsoft SQL server. But as you've all experienced and as everyone has experienced, data has exploded over the past few years. And so just under 4 years ago, the decision was made to build an actual data pipeline that was able to support all of the games instead of a series of one-off scripts that you had to write and maintain for each game.
So 4 years ago, we didn't really know about Kafka, and we had 6 months to get full adoption from all of our game teams. So we basically decided to use a message broker that we already used for interoperability between our different services we run at Blizzard. So we decided on using RabbitMQ and kind of piping everything together with Flume. Flume was more or less our duct tape. Some pros of Rabbit that we really liked is there's a lot of batteries included. Things like policies, publish level confirms, consumer acts. It's extremely stable. There's mature drivers in all sorts of languages, wonderful open source community. And it's written in Erlang, which was developed in the 80s by a telco company and was, their claim to fame was getting 4 nines on telco switches back then. We ran into some problems with Rabbit, and one of those is how it scales. Specifically, a queue can only have affinity for a single CPU. So that was the first problem we ran into. When the queues are empty, things work great. When it needs to spill to disk, it writes to disk very inefficiently, specifically in how it writes the indices. So throughput goes way down. There's usually a point of no return that you get to around 20 million messages where you just have to drop everything. And it's also a con, the fact that it's written in Erlang. It's kind of an esoteric language. We aren't really an Erlang shop at Blizzard. So here's what our first pipeline looked like. Of course, we decided to put it in the World of Warcraft instead of saying where all our real data centers are. But you can see that we had 110 RabbitMQ clusters located all over the world that had Flume consuming on localhost with a custom RabbitMQ source, going to 6 Flumes in our central location where our HDFS cluster is, using the Flume AvroSync. So the biggest problem here was we pretty much only had the Flume memory channel as our buffer, which ended up being about 60 gigs if you added up all the heap and our memory channel size. So in the issue of fiber cuts, or anyone that's had the pleasure of working with the Great Firewall of China, we almost always ended up dropping messages. At the end of it, before we went to Kafka, we ended up with somewhere of 100 plus incidents where we had known message loss because we had to delete the queues. So we used RabbitMQ for the transport. For the actual serialization protocol, we decided to use protobuf. It's something we were already using at Blizzard. That was the big thing, to get everyone to use what we were building in 6 months. We wanted to use technologies that they already had. They already had drivers and the libraries baked into their code, whether it was Java, Python, C++. So protobuf we were able to use to have the game team send their game messages. We were able to use it for schema evolution. But at this point, we still pretty much only used it for schema on read. So a game team would just send us a blob, at which point, a couple months later, when they decided they wanted BI to look at it, they would give BI the proto buff. BI would then generate the code either in Java or in Python to deserialize the raw data that was in HDFS and actually do analytics on it.
Yeah, and we like to refer to Outlook as our schema registry, which we don't recommend, generally speaking.
So this is just kind of a quick graph of our adoption. You can see at the beginning, I'm sure that it looks very similar for a lot of you. Build it, they will come. Some really quick stats. At the beginning, our pipeline received about 3.5 billion events per day. Right now, we're looking at about 20 billion events per day. Probably closer to 25 because they added a whole bunch of messages since Jeff and I came out here. Each product release, they keep on adding more and more messages. And one of the struggles that we have is the game designers generally only care, specifically for gameplay analytics, they only care about decisions they made in the last patch. They want to see if this card that was too powerful is now less powerful, if this boss that they thought was too hard is now easier. And so very rarely do they care about data from 3-4 patches ago. And unfortunately, we don't have a system right now to go and identify the data that hasn't been accessed in 5 months, 6 months, and TTL that data out, or send an email asking, hey, can we delete this data? That's something we're going to be working on in Q1 of next year.
So in 2016, our army of rabbits came under attack on several fronts. Overwatch launched in May of 2016, which Overwatch was Blizzard's first new IP in 20 years, so there was a really high level of anticipation for it. And it was also the first product that was really designed with a data pipeline in mind. In all of our previous products, it was, hey, we're already using RabbitMQ and Protobuf. What if we just serialize this object, send it along, and did analytics on top of that? Whereas with Overwatch, the messages were really crafted from a perspective of, what data do I actually want to send? What questions do I want answered? The end result is that Overwatch sends, Overwatch sends almost as much data as WoW does, and WoW has been around for years. So 3 months after Overwatch launched, the Legion would return to Azeroth in World of Warcraft's latest expansion. And as with every expansion, there are always additional questions that they want answered, and so more messages were added to our already existing data pipeline, which was at that point, fairly oversubscribed and was suffering from the, from network connectivity problems and from bandwidth issues. And if you had too many messages being sent in a region, we didn't have the option of queuing. We just had to say, okay, those messages go away, and now we have to put a little asterisk next to that stat. So we needed something to augment our existing pipeline. Many people, when we started to hit this problem around 2015, said that we could do Flume's job with 4 lines of Spark. We think those people may have been working for the Legion. We're not totally sure. We love Spark, but we think we probably just used Flume in more creative ways than most people had to. For a lot of people, it's, I read something, I write it out. I'm not doing ETL inside of Flume. I'm not using interceptors. I'm not doing any of that stuff that we ended up really using. So we wanted to look around and see like what would make sense. And we felt like Kafka really made sense, but we couldn't rewrite the entire pipeline. Fortunately, Flofka, which originally was a joke name, but has actually stuck, and I kind of like the name, Flofka really made sense for us because we already had the Flume deployments, and we were really comfortable with Flume. And we also, just dealing with like Flume source code, like Flume is actually really easy to read source code. It's fairly well documented. And so we decided that we would move to Flofka and just kind of retrofit our existing pipeline with Kafka. And we were able to do that through this implementation with no message loss, which was kind of a big deal to us because we didn't want to start our new version of the pipeline that we wanted to eliminate message loss on by losing a bunch of messages. So this, again, is the World of Warcraft, but you can see the lines are a lot less crazy now. Like so many architectures, it's, okay, we have these data centers, be they physical or logical data centers, that are globally distributed. And so now, instead of all of those individual data centers going back to the central, which we have in the Maelstrom there, they go to their nearest regional data center, which means the moment that Rabbit can forget about a message is the moment that the regional Kafka has said that that message has been delivered. And that means that at that point, we have 7 days based on our TTL to mirror maker that data back to the central. So if, in a case where there was a fiber cut to Pandaria, let's say, we could buffer 2-3 billion messages and then catch back up. In fact, I think we probably got as high as 10 billion at the most that we were ever buffering. It also means that we now have the ability to, beyond just like network cuts and things like that, just everyday usability, right? So if we're pulling it out of a region that doesn't have great connectivity, We can get 2-3 billion behind during peak, and then off peak we can drain those messages off. Where a lot of the times it was kind of a regular occurrence, like, okay, there's a game launch, it's a Saturday night, and we're just going to tell our NOC that they just have to purge them every hour, and that's obviously not great from a validity of the data perspective.
And just to quickly touch on, we talked about having roughly 60 gigabytes of heap or of cache distributed among the Flume collection layer before. So that went to 60 terabytes for our regional Kafka clusters. So that was a huge win for us, and just the fact that we weren't randomly deleting data during peak or during a game launch was a huge thing.
So one of the other things that Flofka did for us is that it enabled us to write to multiple HDFS clusters for the first time, which simplified our cluster migration process, because our previous cluster migration process was try to copy the data off and then hope that the cutoff point you don't lose too many messages. And now we were simply able to Y off the data, which you could technically do with Flume, but it wasn't really built-in functionality, and there were performance impacts and everything else, whereas with Kafka now, we just get this for free. And so we currently use a customized version of the Flume Kafka channel that is read-only. We do this because we didn't want to deal with Flume's source to channel to sync paradigm, because so many times you end up with either you have a memory channel and you end up losing the data that was in the memory channel, or you end up with, okay, I have something reading from Kafka, writing to Kafka, reading from Kafka, writing to HDFS, and if anywhere along those lines the Kafka part has problems, all of the other parts are going to start rebalancing. So that's why we moved to that version of the Kafka channel. So once we did this, the next bottleneck that we hit was, so we had Flume doing both the ingesting and then writing the data out to HDFS via an ETL process within Flume. What this meant is that our Flumes were opening up 40,000 files each on HDFS, and they were all streaming data into it constantly. And what that meant, especially because the version of Flofka that we use uses the .9 consumer, there's no off-thread heartbeating. So if HDFS took 60 seconds to respond, and then the consumer started rebalancing, all of the consumers would start rebalancing, and then they would all start reopening the data on HDFS. And so you would just end up with this chain of, we would hope after 40, 45 minutes that they would eventually stabilize. But there were times where it was kind of dicey, and I'm looking at the next hour roll, wondering if we're going to make it.
So the scary thing is this would happen every hour. So if it took 40 minutes to get stable, be like, okay, we have 20 minutes to breathe before we go through that
like
entire...
we can get a snack.
Yeah. So to solve this small file problem, we wrote a Spark job called Feed Splitter. How many people here use Spark? Just to get a rough show of hands. Okay. So we knew that Flume was the problem, and that the right thing to do was to remove Flume. But Jeff and I weren't able to sleep. We had 20 minutes of sanity every hour where we could actually think and not be scared that everything was going to blow up. So we knew that we needed to do something right away. And looking into something like Kafka Connect HDFS, Camu, Goblin, that wasn't going to be something we could do in a week. So I spun together this Spark job in a week where Jeff decided to have the Flumes just write out the fat topics. So no longer are we having Flume do the ETL process, identify each unique message, write it to its own directory, partition it by date. Now it just writes out the topic. And here is a quick overview of what Feed Splitter does. So it takes an RDD, for those of you that are familiar with Spark, which contains all the topic data for the batch that is processing. All of our messages contain a unique ID that we're able to use to dedupe. We also have a wrapper, whether that be whether it be a Flume event that has a whole bunch of headers that let us get this data, or we have a custom protocol buffer wrapper that we use also, where we can get the schema, the date that it was sent, the total counts per unique message type, and the total size. From that, we can calculate the average message size and target what we want the file size to be based on our block size in HDFS. And we run it through a custom partitioner, and then we write the results.
So while all of this was going on and we were supporting our existing pipeline, we were also asked to build a new telemetry pipeline that would support operational data for the launch of Overwatch. And while the project got a kind of slow start in 2015, it was around January 2016 that a full team was formed to do this for the launch of a game that was happening in May. So we had a lot of spare time. We would play Nintendo in the office, stuff like that. But what happened is, so we combined the ideas of our legacy pipelines into something that I think really ended up working out well, which is something with schema registry service and a Lambda-like architecture. Our previous incarnation, because the consumption and the ETL and then the eventual loading into something like Elasticsearch would happen in the same thread, we had to artificially scale out our consumers and artificially scale out our partitions. So even for a relatively small partition, we'd still have to go out to like 250, a relatively small topic, we'd have to go out to 256 partitions just to be able to keep up with the ETL. So now, moving to a Lambda-like architecture and microservices, all of those are decoupled. So we can independently scale the consumption and the ETL part and the part that actually writes out to our data stores. The other thing that was really kind of revolutionary for Blizzard is that this is the first time we were able to, at a large scale, collect both client and server data. Prior to this, we would find out we might find out on our forums that there's a problem, or we might see like the server will tell us that we lost 40,000 clients somewhere, but we don't really have any sense of like, did a server go offline? Was it a network connection event somewhere? And now we can narrow it down definitively and say, oh, we had 40,000 people go offline, and it's Time Warner Cable in Topeka. And then we can reach out to that ISP within 15, 20 minutes instead of sometimes within hours and actually resolve the issue. And we're also able to inform our customers better due to that. So in this pipeline, Flume is still being used to write to HDFS, but as in the previous slide, it's responsible for a lot less. It's just taking a binary blob, writing it out into HDFS, and Flume's pretty good at that. So Node RD Kafka, the initial version of our new pipeline was written entirely in Node.js, and we had that 4-month time frame where we had to get this pipeline up and running for the launch of Overwatch. And so they brought in a bunch of developers, and those developers were Node.js developers. And so Node.js is what it was getting written in, because we didn't have time to spin them up on a new language. And it was like, okay, cool, we'll do this and get it done. And one of the problems that we ran into is that the existing open source Node.js Kafka libraries, they caused us a lot of headaches. They were still using Zookeeper for their offsets. And generally speaking, they were very specifically written to whoever the developer was as use case. So if they didn't use a feature that you needed, it was probably not in the library. And the worst part of that is that they weren't really accepting pull requests actively. So even if you fixed it, you couldn't actually get it accepted. So since releasing, we dedicated a developer to writing Node.js bindings for Liberty Kafka, which is a pretty common model to have the Liberty Kafka native library and then write a wrapper around it in the other languages. And it's worked really well for us. Since releasing it on GitHub in 2016, the project has seen over 340 stars, 190 commits, and has contributions from IBM, Wikimedia, and others in addition to ourselves.
So just to briefly recap everything we talked about, we started out with desktop machines with caution tape around them in the corner running Perl scripts to scrape databases and load them into SQL Server. Then we introduced RabbitMQ so we could have some kind of event stream to populate our data warehouse. And then we had all sorts of problems with that, so we ripped out all the RabbitMQ and replaced it with Kafka. The initial thing was, how are we going to get event streams to give our analytics so that they can actually get the game designers answers to the questions that they're asking? But one thing we noticed is after we put this Kafka into place, it was actually really easy to kind of build microservices on top of Kafka, which we couldn't really do before. So this really enabled us to build a whole bunch of different, to support a whole bunch of different data stores, fork off the data, store some of it in Elastic for search and for visualization. We have a custom time series database written in Cassandra. And then, of course, we still use HDFS for long-term. And it's also enabled us to write different data sources. So similar to what other companies do, we have a kind of a REST API, a proxy that sits in front of the regional Kafkas. So we don't have people producing the Kafka directly. We have a syslog RFC 5424 ingest endpoint so that people can just point our syslog at it. Or if there's a syslog appender for Java or .NET, they can just put in our endpoint and send logs to us. And just because of legacy pipelines being legacy pipelines, we still have to support AMQP. We still have code deployed for consoles that aren't getting patched a lot. We still support Diablo 2, which came out in 1996 or something, or in 2000.
2000, I think.
So
now we just want to go over some of the lessons learned that we hit, and some of these are just funny, and some of them are sad. But it's so the first one we hit, and this one was really fun early on, is we had our first production pipeline version of the production Kafka pipeline going. And we were writing to it with one of the open source Node.js Kafka libraries. And we were getting really poor ingest performance, and we couldn't figure out why. And so we started looking, and we realized that the only partition in any of our topics that was getting any data was partition 9. And so it turns out with that particular open source library, if you send null as your key, it will just use partition 9, because I guess somewhere inside of JavaScript, null ends up being a 9. And so that was a really fun one, because we had tens of millions of messages queued up in this single partition, and we just had to wait. We fixed the bug, but we still had to wait for that partition to drain, which took, it was probably hours or days. As with Hadoop, there's always new edge cases. Just like we've experienced with HDFS, you're always going to get that moment where you Google something and it says no results, and your heart kind of sinks. And we've hit a few of those with Kafka, and we hit a few of those with Hadoop, so we were kind of expecting it going in. One thing that we found that was really important to us is we at first we were just said, okay, all of these clusters will be exact copies of each other. They'll have the exact same topics, including the central, and they'll all just mirror into the central, and the central will have a higher partition count to deal with the higher ingest rate, but that'll be totally fine. Until somebody managed to send a bad message through one topic in one region, and it kills all of your consumers for all of the regions that are happening in the central, because none of them can deal with that message. So now it's not just that, oh, my data from Pandaria is no longer arriving, it's priority 1, and hey, we're getting no data anywhere. And so now we shard all of that based on data center, and then we collect from all of those topics in the central. Don't send messages over message max bytes ever, but also definitely don't do it in a while loop. We found that one of our producers was just sitting there and it was trying so hard to deliver this message, it really wanted to get it done, that it just sat there for like 12 hours on this one message, never emptying the queue behind it. And so and it ended up being that the producer had 1 megabyte for its maximum size, and the broker had 1 megabyte for its maximum size. And so there was that 48 kilobyte window where you could really get yourself in trouble, and we managed to find it. And then the last one is, so don't ignore consumer rebalances. We had a tendency like, oh, consumer rebalances, they're like rain, they just happen sometimes. But in a healthy pipeline, you actually shouldn't be rebalancing. Like if one happens, that's fine. But if you're getting rebalances every day around 11 o'clock, then something's happening at 11 o'clock and you probably want to take a look at it. The biggest lesson we learned that for us, bigger isn't always better. I know a lot of people with much larger pipelines, they have very thick brokers, and that's kind of what we went. We went with the same mentality we had for our Hadoop data nodes. We have 60 terabytes of storage, which ends up being 26 because of RAID 10. We have 256 gigs of RAM, and we have 40 logical cores, which is really great for like doing stuff like gzip compression. But the problem that we have is that after tweaking, it can be 5 to 10 minutes to bring up a broker if it's shut down unclean. And the other thing is that we don't actually have that much traffic overall. Like 20 billion seems like a lot to me, but then I see the 1 trillion club, and I'm like, oh, I'm fine. But what we're looking for is a way to, instead of sticking everybody into one big set of giant brokers, we're kind of considering different ways that we can isolate our pipelines, and we'll talk about that a little bit later. So one of the things that we ran into is that naming is hard, but topic naming is particularly hard. If you look at our list of topics, you can see like the evolution of our topic naming as each consecutive product gets a little bit less ridiculous in names, or in some cases more. So we have things like data type, version, product, source, data center in a single topic name because we just want to write a regex that can grab only the topics we want. And then what we're looking at now is we're really excited about record headers. We think this might simplify it for us, and it's something that we had with Rabbit. We had arbitrary keys that we could set in the header, and we also had routing keys and things like that. And so now this will enable us to do some of that once it's supported in our libraries, and once we get some performance testing and see where we're at with it. Partitioning is also somewhat difficult. We weren't very good at the beginning. I'm not going to say that we're very good at it now, but we're better. Currently, we run topics with a minimum partition of 2. Our average partition size now is 20, and our largest partition size anywhere is now 48, which was previously 256 because that parallelization problem we talked about with having everything inside of one process. We currently run with a replication factor of 3 and a min ISR of 2 because we kept running into things where we were running with 2 replicas, and one would go away, and then it would come back, and they would disagree, and we couldn't get anything out of it without just enabling unclean leader election, which is also a valid strategy, and we're not convinced we're right here, but currently, replication factor 3, min ISR of 2. Our central Kafka is 12 brokers with 13,000 partitions, and then our regional Kafkas are 3,000 partitions spread over 6 brokers. They perform reasonably well, but We want to get into a point where we want to look at smaller brokers just to be able to do like red-blue deploys and all kinds of other stuff that we'd like to be able to do. Currently, for monitoring and alerting, we're using, like pretty much everybody else, Burrow. It's really great, and it kind of consumer offsets are the most basic metric that we can use to say that our pipeline's healthy. If our consumers aren't consuming, obviously something's wrong. The current limitation that we really hit with Burrow a lot is that the lag is only calculated at Burrow's request time, and I know that's something that they said they're working on, not at the commit time. So if it isn't consuming at all, it will never advance that lag number, and it'll just look like it's caught up, when in reality it's just reporting 0. End-to-end metrics built into our new pipeline allow us to tell how long a message took end-to-end to process. So we have a client time for when it was sent. We have a ingest time, which is when it hit our ingest processor, and then on the ingest the point where it's loaded into the data store, we have another entry for when it was actually ingested into that. That way we can say, like, definitively, this message took 3 seconds from the point it was in ingest to the point it was written out to Elasticsearch, or this message in HDFS came in at this ingest point and it was written by Flume 6 hours later, or wherever it's at.
So now kind of just to talk about the future. For us, we can only think ahead like 2 quarters. So this is what we're doing Q4 and Q1. Number one, we talked about Flume. We kind of reached the end of our free lunch with Flume. So now we really need to find something that runs in batch. We don't need real-time analytics on the HDFS side. Other data stores take care of that for us, like Elasticsearch and Cassandra. So we really just need something dead simple that runs in batch every couple of minutes or once an hour, and writes out everything to HDFS, splits it by message type, partitions it by date, similar to what Feed Splitter does. So we're going to be looking at Goblin, Camu, Kafka Connect, custom Spark application. If anyone has experience in this and wants to point me in the right direction, that would be awesome, since I haven't started researching it yet. We're going to continue using Flume for our legacy pipeline because what it does is so simple, and a lot of our problems, a lot of the edge cases we ran into with Flume are specifically with the HDFS sync and the bucket writer. So when all Flume has to do is consume from RabbitMQ on localhost and publish to Kafka, it actually works extremely well. We have some uptime numbers that I'm afraid to share because that would mean we aren't updating our OS often enough, because Jeff and I are crazy about that kind of stuff. So the other big thing is Jeff talked initially about kind of isolating on the topic level, where we're running into issues with bad messages getting into a topic on the central Kafka. We want to take that a step further and kind of go the Netflix route and really be able to have dedicated, isolated clusters that are kind of all over the place and kind of use the cluster as our scaling point instead of the number of brokers. We currently have a software as a service thing that we wrote that runs on top of Docker, where someone can go click a button and get a fully dedicated, what we call the telemetry development kit, Kafka, Zookeeper, Cassandra, Elasticsearch, all the bits and pieces that tie all that together, an instance of Zeppelin to see what the data is going to look like in Hive. And we want to figure, right now that's just deployed on a single node, a whole bunch of JVMs on a single node. We're thinking that we might be able to actually have that deployed and coordinated on a whole bunch of nodes and be cloud agnostic, so we have the ability to deploy it both in private and public cloud. Obviously, that involves a lot of stuff, a lot of moving parts. They talk about it in Netflix talk. We need service discovery, we need automation, we need to write a routing service. So if anyone's kind of going this route or has some ideas about ways we should approach this, I'd love to talk to you as well.
Okay, and we have some links to things mentioned and things not. First, obviously, is NodeRD Kafka, which is our Node.js Kafka library that I discussed earlier. Patches, as always, welcome. Burrow from LinkedIn, which is what we monitor consumer offsets with. And JMX-term, which is how we get the metrics out of Kafka and Zookeeper and into our custom metric system. The last one I didn't mention, but in the past month has saved me enough times that I wanted to give it a shout out, which is the Kafka utils from Yelp, particularly around being able to clone and manage consumer offsets and consumer groups. That has been really helpful to me in my current projects. And last, the required slide that we're hiring. We have a giant orc. I don't really have to say much else. Like, there's a giant orc right in the middle of campus. But so if that excites you, then you should probably go to our career site. We're hiring Java Scala devs, operations people, product managers, and various other positions. And feel free to give us a shout if you are interested. And I think now questions.
I think you guys mentioned you guys have the issue of the group rebalancing. Could you give more details about how you guys mitigate that issue?
So it's been different for each case. So in sometimes it was, okay, the process that was consuming was just, it's in garbage collection, or it turns out that one of our processes that we didn't have as much monitoring on as we should have is core dumping at noon every day or something, and we just didn't pick up on that. So each time we had additional monitoring, and then each time our pipeline finds new things to break that aren't monitored. And so that's been a constant struggle to add enough monitoring for that. But usually it's I lost its connection to Zookeeper, a garbage collection happened, something core dumped somewhere, an operation to writing into Elastic, which usually takes a few seconds. Every 10 billion messages, maybe one takes 60 seconds, and that causes the consumer group to time out. And so each one has been a different one. I wish there was a pattern to them. That would be really great. Anybody else?
Hi, thanks. I got a chuckle out of the burrow thing because it's very, very true. So one of the things we're looking to do right now is, and I don't know, I'm trying to find any other people who may have done this, but we're looking to implement like basically we want per topic monitoring, but we want to know if anyone's successfully done it with the Kafka authentication, like access control lists and stuff. So I don't know if you guys have any experience with like the TLS, security SSL, like all of that stuff, and Burrow, because I don't think it's going to work if I turn that stuff on.
Yeah, so we haven't looked at the ACL stuff extensively yet. We're mostly, because we're still on .9, we're working on that. It's a work in process, but we weren't comfortable deploying that yet, so we haven't really looked into it. But I know that the capability is in there. But most of our monitoring does come from Burrow, and so we have it down to we visualize in Elastic, at the partition level and at the consumer group level, all of this data, but our per topic metrics are still limited to basically whatever we can get out of the broker and whatever we can get out of Burrow.
You guys mentioned the JMX term integration. Where do we feed that data into? What kind of graphing tools? And you also use Burrow. So how do you what do you use each for?
Yep. So in the case, Burrow is strictly for consumer group health, and that both cases are kind of similar. So with Burrow, we just have a service that reads from Burrow once a minute, scrapes all of the data, and then uses. We have a second copy of our pipeline. So we have the telemetry pipeline, and then we have the telemetry pipeline, and that just monitors the first one. And so Burrow, we have a Python process that uses our Python SDK to send all of the data from Burrow once a minute that ends up landing in HDFS and Elasticsearch, and then we have alerting and monitoring based on that. Similar, the JMX values, the JMX term, we wrote a custom output. One of the developers on our team wrote a custom output for JMX term that outputs to that same system.
Using our Java SDK.
Using our Java SDK. And then that just gives us, all of the kind of standard metrics that somebody would monitor through JMX for Kafka. I'm sure I stole like Wikimedia's list of metrics or something, and that's basically what we're monitoring right now.
Any more questions? Oh.
Horde or Alliance?
For Nomergon.
I'm Horde.
I'm actually a Tauren right now because my friends are, but my heart is in Nomergon.
Great. Okay, let's thank the speakers again.